we will want to know basically from the sound that created basically is by means of vibration and resonance, how it will deform the so-called the 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 body, okay, the body of your guitar itself, okay. So in this case, we want to, if we can know first, we want to know the natural frequency or the dynamic characteristics or dynamic behavior of this guitar, okay. So here we are interested on this particular, sorry, we are interested on this particular surface, okay? The deformation of this particular surface when you have a force, basically a harmonic force. When I say force, it's harmonic force, meaning 1 megapascal. Okay, 1 megapascal. Okay, of harmonic force. So probably my P is P naught, which is 1 megapascal. Sine 2 pi ft. Okay, my f I can vary, okay, differently. Okay, then I will want to see the response at this particular so-called guitar itself. What is the response? So to do that, to know the response itself, okay, we want to know the response or frequency response itself. We need first the characteristics, the natural frequency and mode shape. So remember, we say that from here, okay, to know the X itself, right, we need to know the natural frequency and mode shapes. From there, only we can use mode superposition method to find our X1 until Xn, meaning the notes deformations. So how it works, basically you have to first performing the model analysis to get its natural frequency and mode shape. With these informations, natural frequency and the mode itself, then only we can find the X. So we want to find the response. Here is the X over different frequency. So my F can basically I vary my F from probably here, let's say 0 to 4,000 hertz. Okay, what will be my X? Okay, over the frequency. X here is referring to the displacement in terms of this surface. Okay, it could be any surface. So here is this surface. To perform these particular case studies, right? First you have to perform model analysis. You just remember the flow. You perform model analysis, you get the model parameter or the dynamic characteristics in terms of natural frequency and mode shapes. Then only you need to use this to determine the response. Here is talking about the harmonic response. So now first you have to perform model analysis. Okay, you can perform model analysis here, right? So you get your natural frequency, you get your mode shapes, respective mode shapes. Then the next one is to find the frequency response, the response at different frequencies, what it means here. So here you are doing this harmonic response. Okay, so this harmonic response, it have to be, of course, you have to use the solutions from the model. What I said, the solution means the natural frequency and mode shape. So it have to be shared with this harmonic response. The result from the model have to be shared. So you have to share until the solution. So you will see something like this later on, right? So here, engineering data, of course, material is a wood. So okay, you have to add your own materials. Then modeling, you can use design modeler as well as what we call space plan to model it. So the focus here is I want to show you is the results, more towards how you set up and how to interpret the results in terms of the analysis itself. All right, so you build your M, you build your K, then from the discretization of your elements, then you have your natural frequency as well as the mode shapes. So first you have to assign a material is a wood, right? So one material you don't have contacts, then but meshing here I'm putting just a 5 mm, that's it. Okay. Then you need to put a boundary, right? So under model, you don't have load, it's a free vibrations, so you don't put load, but you need to put a boundary. So the fixed support is at the back, right? Right? Then you can actually, once the boundary is done, then you can actually start the analysis. So under analysis setting, you are asked to find 10 modes. So you put in 10, okay? Maximum mode to 10. So the deformation here is your mode shapes. So here later on it will solve. So you have to put insert deformation, total deformation. So the deformation here is the values we said that it's a mode shape, right? So it's a relative. So this value have no meaning. The contour itself telling you how the movement relatively. So it's a mode shape. So this mode shape, this value is non-absolute. Okay, so once you have add on, okay, so you add total deformation, then you can select which mode you want. So it's mode 1, then you add another one is for mode 2, you add another one for mode 3 until first 5 modes. Okay, then you solve it. Okay, so if you click solve it, then at the end you have this a list of frequency up to 10. Okay, because we set 10 natural frequencies, so we get a list of natural frequencies, and these are the corresponding mode shapes. So the mode shape we only set 5. Okay, of course you can set to 10, but here we are looking into the first mode. Okay, 1038.4, 1038.4. This is how it will deform at 1038.4. Okay, it's mode shapes, and this value have no meaning, so just the relative motions. You know that, okay, the maximum deformation will be at here. So how to interpret the result? Okay, this is what it means. 1038.4 is its first natural frequency. So from 0 to 1000 have basically known the very first natural frequency happened at 1000 something, 1038.4. Right? So you see that is how it will vibrates. Okay, when you have an excitation, okay, at a frequency of near to 1038.4, then this is how it will vibrate. Okay? Then if you look into the second mode shapes, so this is how it will vibrate. Okay, here more deformation compared to here because the maximum is at here, right? And of course you can look into the third, fourth. So if you have these informations, omega mode shapes, right, then we can perform our so-called force vibrations or harmonic excitation, harmonic response, right? So under harmonic response, of course, you will see that because we share with model, right? We share the solution from model. So here we are sharing the informations, right, from model. You'll see here, right? Then the analysis setting, of course, uh, uh, the response, okay? We want to know from, because you see the natural frequency is started from 1038 until 4000, first 10 modes, right? So if you are looking into the response at below 1000, you don't see the effect of frequency. You will see very low vibrations, okay, because it doesn't go near to the natural frequency because the first natural frequency is 1000. So we want to see the effect of frequency. So probably our setting here, we put 1000 to 4000. Okay, you can put 1000 to 4000. So this interval is how fine you want it to perform. Okay, if you put more, okay, if you put 1000 to 2000, interval is 100. So what it means here, you have every 10 hertz. Every 10 hertz, you have a point. So I can have 1000, 1010, 1020, 1030 until then add with 10 right? The interval of 10 hertz to get up to 2000. Okay. So if you want to put 1000 here interval, then you have a 1000 point, data point, right? So it's 1001, 1002 until 1999, 2000. Right? So that is what it means. So of course, if you have very fast interval, then you will wait longer time the solution, because every single data point, every single interval is one solution, right? So you have more solution interval, higher solution interval, then you have a longer simulation time, right? Computation time. All right, so here I just put 1000, 2000. We want to see the effect of the first, second modes over different frequency. Of course, you can go up to 4000. So you can see the effect of the effect of response frequency. natural frequency with the excitation frequency over the frequencies, I mean up to 8 modes. So here I'm just taking look into 2 modes, right? So the example is stated 1 to 3,000, 1 to 4,000, 1,000 to 4,000, and 300 intervals, solution interval. So here you have to wait 3 times longer, but now I'm using just up to 100. So remember that under harmonic response, we want to calculate X. Okay, we have the natural frequency and mode shapes. We need to have the force. Right, we need to put in the input of the force. So here the force is along this surface 1 megapascal. Okay, then once you have done this, okay, then you can add what is the frequency response. Okay, frequency response, we want to look into the deformations, right? The response in terms of displacements, deformation over different frequency. So whatever that you get later on, so this is the response over frequencies. Oops. So this is what you will observe, okay? From 1,000 to 2,000, every single point of 100 intervals, solution interval is 10, right? So you have 1, 0, 10, 1, 0, 20, 30, until 1990, 2000. Okay, total of 100 data point. Okay, so with this 100 data point, you determine the X. Okay, at omega equals to 2.1010, what is the X? Omega equals to 2.1020, what is the X? So you have to calculate 100 times, right? To build this, what I said, the frequency response that you have observed just now, right? In my slides. Okay, so this meaning to that, you see that there is one peak at here, very high vibration at here, which is at around 1040, and another one is around 1690, right at here. See or not? The peak is 1690 and 1030, 40. Right? Why is high vibrations? Why very high amplitude at here, at this frequency? Because your omega 1040 is very near to your first natural frequencies, 1038. Because I don't have 38 intervals, okay? So 40 is my intervals. So 10 hertz is my interval. So the nearest is 1040. Is near to this 1038.4. So you have a very high vibration amplitude. Okay, at around 38.57 mm. The other one is 1690, right? Why? Because it is near to my second natural frequency, 1687.7. Right? So that is why you get this particular response over different frequencies. All right. So here's the solution method. We are using mode superposition, if you are aware of. Okay, this mode superposition, basically we are getting we are adding, okay, the contribution from different modes into our response, our final response X. Okay, so that is what you can obtain from harmonic response. So from there, we know the exact response, okay, that will be contributed or will be created when it at different frequencies. So it's not a flat or constant response. X, your X is changing over frequency. Is it how close is it to its natural frequency, because you have this resonant constant. All right. So in this particular case, you can also want to go into its animation. So you can also find, let's say, directional deformations, right? So in z-axis, okay, because we want to see the z-axis itself, body, if you just want this body, this face itself, right? And at what frequency? If you want to look into 1040, which is one of your data point, it have to be, this number have to be one of your data points, okay? So you have 1040, right? So if you can solve it, so you can find that it is the deformations, right? Around 151, okay? 151 mm in this case. You see, that is at 1040. Right? You can actually find the deformation of this space. Right? So this is using average. So this is using the maximum, the average. So if you want to find response deformations, then if I'm using this particular phase itself, I'm using its maximum itself. The direction is z-axis. If you evaluate it, because it's already soft, right? So you can see that, yeah, it's 151.32, and it is similar with what you have observed here. Okay. Right? So that is average value. Just now 38 is the average values. Okay, so this one you can actually see how it moves, right? Because why it moves like this or why it deformed like this, because it's very close to the first natural frequency. The main contributor of this particular response is the first mode. Okay, so how if I go in between? Okay, the first and second. Okay, 1040 and 1690. Right, so if I put 1500, okay, what will be my responder? So if I put 1500 in between, so you have a contribution from, I would say, from the two two modes. Okay, all will contribute from the closest mode, I would say. So here you will see that it will be contributed by two. You see the motions of this particular plate cell is contributed by the first mode and the second mode. You see, it's similar. How it behaves is similar. Contribute by this mode as well as this mode. All right, so you have a similar motions. Okay, contribute by this, because these two is the closest to 1500. But in the case of 1690, then it will be vibrating mainly by the closest mode is still there, but then it's mainly by the second, what I call the second mode dominates. Right, so that is very similar to our second modes. Right, the deformation at here is not that much anymore, which is similar with our second modes. Right, so if you want to go to 2100, so your solution interval have to cover up to 2100. So far I can only cover to 2000, so which is within this mode and this mode. Okay, so I can only see the contribution from these two modes itself.